Hello everyone, welcome to the second lecture of this NPTEL course on Riemannian geometry. So last time we looked at two possible generalizations of the sum angle property. One of them was that for a curved triangle, let's call it A1, A2, A3, if the external angles are epsilon 1, epsilon 2, epsilon 3, then the sum of the external angles plus the total turning angle of the tangent vector to the edges, because remember you are looking at a curved triangle. So the sum of the external angles plus the total turning angle, that turns out to be exactly 2 pi. Okay. So now in this lecture I would like to address the important question on how do you actually calculate this turning angle. So it turns out that this turning angle is as one would expect intimately connected to the geometry of the curved edges. So we would like to understand a precise relation between this turning angle and the geometry of the curves that make up the edges. Okay. So so I'll already give away what the answer is. The answer is going to be that the turning angle is related to the curvature of these of the plane curves. So of course if you have straight line edges between the two vertices, then this quantity is going to be 0, and we get back our sum angle property from high school. Okay, so in order to motivate curvature, I am going to draw two pictures, or at least in order to motivate how to compute this turning angle, I am going to draw two pictures. So one is, let's say I have a curve and I am traversing the curve in this direction, and the second picture I have the same geometrically the same curve, but now I am traversing it in the opposite direction. So at each point throughout this lecture I am going to, so this is going to be my standard assumption that gamma is going to be a smooth path which is arc length parametrized. So what does this mean? This means that the speed of the curve is always going to be 1. Okay, this is going to be a curve with unit speed. Whatever I am going to do today, all the formulae that I am going to write down, one can have analogous formulae for curves that are not arc length parametrized, but they are a bit more complicated to write down. So to simplify matters, I am always going to parametrize my curve, and given any smooth curve, this is an exercise that one comes across in multivariable calculus. One can always reparametrize that curve in order for the curve to have unit speed. Okay. Alright, so now let us look at these two curves that I have drawn. Let us say they are arc length parametrized. Then at any point here I look at the velocity vector, that is going to be a unit vector, a vector with norm 1, and I am going to call that T of S. So that is the unit tangent to my curve. Similarly at the same point for the other curve, I am going to have this T of S pointing in the opposite direction. Okay. Now I am working in a two dimensional plane, so at any point if I need a basis for my vector space, I essentially just need two orthogonal vectors, right. So I already have one unit vector, namely this velocity vector at this point. What I am going to do is I am going to rotate this vector in an anti-clockwise direction by an angle of pi by 2. Okay, and I am going to call the resulting vector n of s. So I will do the same thing to this curve to end up with this vector, right. Now for the first curve, if you notice the curve is bending away from the normal. So if you calculate the acceleration vector, so let me do this calculation. So this is a simple sort of observation, is that if you calculate the acceleration vector, that's always going to be perpendicular to the velocity vector. Okay, why? That's a simple calculation. The velocity vector has unit speed, so if you differentiate gamma dot of s squared with respect to s, you are going to get 0, because that's a constant, that's 1, right? On the other hand, by the product rule, this is the same as the inner product of the acceleration vector with the velocity vector, okay, which implies that the acceleration vector is always perpendicular to the velocity vector whenever your curve is arc length parametrized. So in this picture, the acceleration vector is going to be either in the direction of the normal vector n of s or the opposite direction. For the first picture, because the curve is bending away from the normal vector, the acceleration vector is going to point in the opposite direction to n of s. On the other hand, here the acceleration vector is going to point in the same direction as n of s. Okay, so this sort of situation, I say that my curve is negatively curved, where the acceleration vector points away from the normal vector. When the acceleration vector points towards the normal vector, I call that curve positively curved. Okay. So this is as far as the sign of I mean the sign that I want to assign whatever is my definition for curvature. What about the magnitude? So in order to guess what the correct formula should be for the magnitude of the curvature, I sort of take an example from physics. So suppose you have a car that's traversing on a circular track of, let's say, radius r, right, and let's say the speed is constant. So the speed is constant, and let's say that constant is 1, right. So that means my track is arc length parametrized. Then we learn in physics that the acceleration, the magnitude of the acceleration, is basically given by the speed squared divided by the radius of the circular track, right. So in this case it will be 1 by r. Now you think of a really large circle, so r is really big, then of course if you have a really large circle and if you are, let's say, an ant on that circle, then of course around you do not see much of curvature, right. So that means really large circles tend to have smaller curvature, at least intuitively. In any good notion of curvature, a large circle would have a smaller curvature. So in some sense this factor 1 by r is like the curvature of my circle of radius r. So this motivates the definition for the magnitude of the curvature. I basically just take my arc length parametrized curve and calculate the magnitude of the acceleration and call that the magnitude of the curvature. Okay, so that's one thing. What about the sign? So I already explained pictorially what the sign of the curvature should be, but this involves an anti-clockwise rotation of the tangent vector, right. So let us first try to make mathematical, or put that into some, I mean, let's have some rigorous formulation for what anti-clockwise rotation means. Okay, so let's first address that problem. What do you actually mean by anti-clockwise rotation by pi by 2? Okay, so from elementary linear algebra we know exactly what the rotation matrices look like. So they basically look like cos minus sine, sine and cos. So here I want my angle to be pi by 2, so I fill that in. So then you are going to get this matrix 0, minus 1, 1 and 0. Okay, so so let's do a sort of sanity check. So consider the two basis vectors. E1 the standard basis vector in the x direction and E2 the standard basis vector in the y direction. Let's apply this matrix J to E1 and E2. So it's a simple calculation. If you apply J to E1, you are actually going to end up with E2, and if you multiply J to E2, if you apply J to E2, you are going to end up with minus E1. So in picture, this is E1, this is E2. So E1 is going to be transformed into E2. E2 on the other hand is going to be transformed into minus E1 by multiplying by this matrix. So that makes sense, right, because anticlockwise rotation of E1 by pi by 2 should give you E2, and anticlockwise rotation of E2 by pi by 2 should give you minus E1. So, so when I say anticlockwise rotation of any vector by pi by 2, I actually mean just multiplication by this matrix J, right. So then for my curve gamma, let T of S be the velocity vector. Since it's arc length parametrized, this is a unit vector, and I define n of s to simply be j applied to T of s. Okay. Then by my little calculation earlier, I know that the acceleration vector is perpendicular to T of s, but T of s and n of s span R2, right, because they are orthogonal vectors, because you know n is the rotation of t by pi by 2, so these are orthogonal vectors, and R2 is two dimensional. So if you have two orthogonal vectors, they have to form a basis for R2. So this implies the fact that the acceleration vector is perpendicular to the tangent vector implies there is no component of the acceleration vector along T of s. So this implies that T of s will be some number k of s times n of s. Okay. So this number k of s is what I define to be the signed curvature of my curve. Okay. So let's write that down as a definition. So the number k of s is the signed curvature of gamma of s of this curve gamma at the point gamma of s. Okay. And then one thing to note is that if you take the absolute value of the signed curvature, so you take the unsigned curvature, then clearly that is just going to be the magnitude of the acceleration vector, because n of s is a unit vector, right. So the magnitude of this signed curvature is the acceleration vector, which is the magnitude of the acceleration vector, which is what our motivation was with this picture of a car traversing a circular path, right. So at least conceptually this is a sensible definition to have. Okay, but I originally started with this question of how do you actually calculate this turning angle, right. We shouldn't forget what our final goal is. It's in order to come up with a sum angle property for these curved triangles. So the question is, how is this curvature actually related to the turning angle? Okay, so here's my sort of little claim that if gamma is a short curve, I'll explain what I mean by a short curve, and theta s is the argument of the velocity vector. So let's draw a picture. So let's say your curve gamma is something like this, and the tangent vector, so at this point you have this unit tangent vector T of s. We draw a vector parallel to that at the origin, then the angle that this makes with the x axis, that is going to be theta s, right. So so then the conclusion is that the sine curvature is precisely the first derivative of theta s. So remember, the total turning angle was basically how much your velocity vector turns, right. So that is obviously by the fundamental theorem of calculus obtained by integrating the derivative of theta. So what this actually tells you, at least for short curves, again I'll explain what that means. For short curves, integrating the sine curvature actually gives you the total turning angle. Okay, so why do I have this caveat of a short curve? So let me make a remark. So recall that that the argument function can usually only be defined as long as you remove a half ray, right. Otherwise there is no way to define a continuous argument function on all of R2 minus the origin. Of course at the origin one can't tell what the argument is undefined, but it turns out that even if you throw away the origin, there is actually no way to define a continuous argument function on all of the punctured plane. This is actually a very nice exercise in point set topology. So if you haven't seen this, it's a good thing to think about. But we learn in complex analysis a way to get around this is by just dropping a half ray, right. So typically the convention is that you drop the negative x axis, and then the argument function takes values from minus pi to pi. Okay. So I need the curve to be short so that T of s, as s varies, never crosses the negative x axis. Okay, so for instance, so cannot have things of the following form. Something like this, right, because here my velocity vector is doing a full rotation, so at some point it will cross this barrier of the negative x axis, right. So I don't want something like this to happen. All right, so that is what really I mean by short curve. I'm going to be vague here, but this is essentially what I mean by gamma being a short curve. Okay, so let's do the proof of this this little claim. So the point is that if gamma is a short curve, let gamma dot of s be as usual T of s, and let the components of T of s be u of s and v of s. Okay, right. So gamma being short actually implies that the argument of the tangent of the velocity vector is not only continuous but is actually smooth. Okay, so I can take all derivatives that I want, and in fact then up to a constant theta of s is precisely some constant plus it's precisely the arc tan of v of s by u of s, right. Theta of s is the argument of t of s. So given any vector, the argument up to a constant is just essentially I am using the fact that tan theta is the slope of the vector. The slope of the vector is the y coordinate divided by the x coordinate. So to calculate the argument up to a constant, it's just the arc tangent. Why do I have this constant? Because the arc tangent usually takes values only between minus pi by 2 to pi by 2, whereas the argument, depending on whether you are in the first, second, third or fourth quadrant, can take any value between minus pi to pi, right. So that is why one has to normalize with a constant. Anyway, the point is that I can now differentiate this. So if you calculate theta prime of s, that's just going to be that's just elementary calculus. It's going to be u squared by u squared plus v squared. So that's essentially I am using chain rule. I am first differentiating arc tan and then differentiating the quotient inside. The derivative of the quotient inside is u v prime minus v u prime divided by u squared. Now u squared plus v squared is equal to 1. Why? Because that's the norm of the tangent vector, and the norm of the tangent vector is 1, arc length parametrized, right. And similarly these two cancel, so in the end I only have u times v prime minus v times u prime. Okay. So I want to claim that theta prime is actually the signed curvature. So let's understand what is n of s. N of s is j applied to t of s. So that's this matrix 0 minus 1 1 0 applied to uv. So you just do the matrix multiplication, that's going to be minus v and u, okay. On the other hand, what is the acceleration vector? That is simply u prime v prime, okay. So remember how we defined the signed curvature. The signed curvature k was simply what you need to multiply n of s with in order to get the acceleration. So that means u prime was minus k times v and v prime ought to be k times u, okay, by the definition of what the signed curvature is. Okay, so now recall that in the previous page we calculated that theta prime would be u times v prime minus v times u prime. So instead of u prime I plug in minus k, instead of v prime I plug in k. So this is going to be k times u squared plus k times v squared, which is k times u squared plus v squared. But again u squared plus v squared is the norm squared of the tangent vector, which is 1. So this is k. So theta prime is precisely k. So this proves our little claim that theta prime is actually k. So the way I stated it, it was only for short curves, but in fact there is a beautiful generalization due to Hopf. It's a very classical theorem, I think from the 1930s or maybe even earlier, which actually says that this observation of ours is more or less correct even for curves that may not be short, right. So I mean for instance, I mean as a consequence of what we did, if you have a short curve, then the integral of the signed curvature will basically be theta b minus theta a, but theta being the argument of the velocity vector, this is basically just the total turning angle of T of S, right. So of course if you take a complete rotation, that is no longer a short curve, so you can't really apply our calculation here, but suppose formally at least we expect the corollary to be true even if the proof does not work. Our proof does not work for long curves. If we assume that the corollary works, then if you have a closed curve, one would expect that the total curvature on that curve would then integrate out to 2 pi, right, because that is sort of the your tangent vector will make an entire rotation. So one would expect that this is actually 2 pi, and of course if you keep going around the curve again and again, then of course it would be some integer multiple of 2 pi. So it turns out that even though our proof does not work, the statement that I just said is actually correct, and this is the content of this very beautiful theorem due to Hopf, and very classical theorem, that if gamma is a smooth, simple. So what does simple mean? Simple means that if you restrict it to the open interval a to b, this is actually 1 to 1, okay. So it does not, the only point at which it intersects itself is at the end points, okay, and closed. So that means it does intersect at the end points. So if you take a simple closed curve which is smooth, then the total integral of the curvature is actually going to be 2 pi, okay. So if you are interested in the proof, it is in Lee's book on Riemannian manifolds. The proof is also there in many other classical books on the geometry of curves and surfaces, right. So I think you can take a look at maybe Docarmo's book on curves and surfaces. It must have a version of this. There are many other books that have a proof of this, because it is a very classical fact, right. Okay, so that brings me to really the generalization that I want. So before that, let me make a definition. So a polygon P in R2 is basically a piecewise smooth curve. So that basically, I do not want to write down the definition, I am sure you must have seen this before, but a piecewise smooth curve essentially means that it is almost a smooth curve, except it is allowed to have a finite number of corners, right, where the velocity vector makes an abrupt jump. Okay, so it is a piecewise smooth simple closed curve. Simple closed curve. So just to draw a picture, you might have something like this. So here the picture has sort of 4 vertices that I'll denote by A1, A2, A3, A4. Okay. So the boundary is the polygon, the inside part. So it's a famous theorem in topology called the Jordan curve theorem, that any continuous simple closed curve must divide the plane into 2 regions. One is a bounded region, one is is a non-compact region. The bounded region is what I call the interior of the polygon, right. So now I can finally state my the generalization of the sum angle property for curved triangles or curved polygons in the plane. So this goes by the name of local Gauss-Bonnet theorem. In R2. Okay, so this says the following: let P be a polygon in R2 with external angles measured with the right sign. So what do I mean by measured with the right sign? So let's look at the external angles here. Sorry. Right. So the idea is that that if your tangent vector turns in the anticlockwise direction, you count that external angle as positive. Otherwise, you count it as negative. Right. So you have to be careful. You have to measure the exterior angle with the correct sign. Then it turns out that the sum of the external angles, sorry, I should then the sum of the external angles, so let's say plus the integral of the curvature, this is going to be 2 pi. Okay. So that's what is called as the local Gauss-Bonnet theorem in R2. So in the next class, I want to talk about the local Gauss-Bonnet on curved surfaces. So instead of R2, which is of course this flat plane, I want to consider the local Gauss-Bonnet on curved surfaces. All right, so maybe I'll stop here and I'll see you in the next lecture. Thank you for your attention.